Okay, so we've talked about how we find a linear relationship, or how we find if there is a linear relationship um, between variables. So now we're going to start asking statistical inference question about that. I mean, is there really, or could the pattern just be by chance? And what's the margin of error in our estimate of the slope? And that's what we'll be pursuing. We're moving on to chapter 12 now. And so this is the last chapter of the textbook. And so we're going to start this off with an example. Here is the data from Old Faithful. This is all 222 recorded eruptions in 1 month. The least squared regression line for the population data has been added to the scatter plot. Its slope is 10.3. And this is what's known as the true regression line because it uses the entire data points. And so the slope is 10.6 and the y-intercept is 33.9. And so for every minute that the eruption goes up, the interval between eruptions increases by 10 minutes. So suppose we take an SRS of 20 eruptions from the population and calculate the least squared regression line y hat equals APBX for the sample data. How does that slope of the sample regression line relate to the slope of the population regression line? And so here, if you see the little green dots are the SRS of 20 from our overall sample. And what you see is we start to get variability in the slope and the variability in the y-intercept and variability in the slope. And so this is going to be another example of a sampling distribution where we do this again and again and again and again. And here's an applet if you want to go try it on your own. But basically, they did this in the computer. They took a 2,000 SRSs of sample size 20 from the Old Faithful data. And we see our old friend that's approximately normal. It's definitely symmetric. It's definitely unimodal. And what we see is the center is very close to the true value. The standard deviation is 1.31. And later on, we're going to find out that that's very close to what the true value is of, remember, this is a simulated sampling distribution. This is not the true sampling distribution. The true sampling distribution would be every single possible sample. So the slope and the intercept of a least squared regression line are statistics. That is, that we calculate them from sample data. These statistics would take a somewhat different value if repeated the data production process. To do inference, think of A and B as estimates of unknown parameters, alpha and beta, that describe the population of interest. So what we're saying is that we've been doing this, and the true regression line is that, alpha and beta. So in order for us to do inference on regression, there are conditions that must be met. Remember earlier we had conditions for all our sampling, if we were doing a p-test, or a t-test, or a z-test, and random, normal, and independent. Now we're going to create a new one. And so for linear regression, we're going to use liner. And you must check all 5 conditions. Linear. The true relationship between x and y is linear. So in order to, independent. All individual observations are independent of each other. Normal. For any fixed value of y, the response, for any fixed value of x, the response y is normal. Equal variance, and this is basically saying, this one's tricky. And the standard deviation of y is the same for all values of x. And random, the data come from a well-designed random sample. So how do we check those? Oh, by the way, here is the showing the equal variance. Is that there's this smattering around the points is the same regardless. That's why when we're talking about residuals, we don't want to see cone patterns in the residuals because it violates this condition.
Students who ride bus 358.
Excuse the interruption about the bus.
Because bus 130 is on the way to pick you up. Again, students who ride bus 358 need to report.
You got that on their bus pickups? That's important.
Bus 130 is on the way to pick you up. Thank you.
And you can refer to this picture in your book, but it's basically saying that for any value of x, there's as x's get bigger or smaller, the variation in y's does not increase or decrease. So how do you check these? Because that's the thing, is you're going to have to prove that you checked them. So for linear, you're going to have to look at the residual plot and see if there's a pattern in the residual plot. And that's how you check the linear. For independent, look at how the data was produced. And if we sample less than 10, if we're sampling without replacement, then we can't sample more than 10%. Normal, look at the normal, do a normal probability plot of the residuals or a histogram or a stem plot and show that there's no clear skewness in the residuals. Equal variance. Basically, this is we don't want to see a cone pattern in the residuals. We don't want to see, once again, no patterns in the residuals at all. And then randomness is just how it was produced. And so that's what we'll get into. In next class, we'll be getting into the confidence intervals and I lost my train of thought here. The confidence intervals in the 4B.